Hello, this is Paul for Foresight Tech. In this video, we are going to deal with the logarithmic differentiation, which is an important method to find the derivatives of complicated functions. Let's see the material. First, I will introduce the method of logarithmic differentiation. Next, we will practice two questions together, about how to use the method. Then I will introduce a proof for the general power rule we learned before using logarithmic differentiation. Last, I will introduce a very famous limit expression of Euler number E or natural number E. Okay, so let's see. And here is the first. What is logarithmic differentiation? What do we need to do with logarithmic differentiation? Of course, is still going to find the derivative, but this time is find the derivative of a complicated function involving products, quotients, or power. You remember? Let me highlight this, and we're going to use this to deal with this complicated. If we have a product, if we have a quotient, if we have a power, okay. And then we're going to use logarithmic differentiation. What does logarithmic differentiation mean? We need to use the logarithmic function. Okay. And do you remember when we learned the log functions? Log function has an important property, and it can help us to simplify products, simplify quotients, simplify powers. Do you remember? Okay. If you remember that, okay. So logarithmic or how to perform. So we have 2 or 3 steps. Okay, so can we see? Let me highlight. Now is the logarithm. For these double functions, the first is simplify the function by taking logarithm both sides. Usually we take a natural logarithm because natural logarithm is simple. Okay, what does this mean? And this step can help us to simplify the function. Okay, after simplify the function, and then what do we get? We will get the implicit equation. You know what? Implicit equation, we can use the implicit differentiation method, right? To find the derivative. Implicit differentiation has 2 steps, okay? So the first step, differentiate both sides. The second step is our linear equation for dy dx. If I put these together, and usually we will say is 3 steps. Okay, can you see? The first is take a log both sides, okay, to simplify the function. The second is differentiate both sides of the implicit equation. The last step is resolve the linear equation for dy dx. Now we are going to practice 2 questions, okay, so about these procedures. We call the logarithmic differentiation. Can you see here? The first, we have a function, and this function looks not simple. Okay, is x raised to the power of x. This is not a power function. This is also not exponential function. You see, it's kind of a composite function. Of course, you can go into the composite function, then use chain rule. But here in this video, I will use the logarithmic differentiation, okay, to solve this question. And how to do? You know, the first step, simplify by taking log, right? I will going to take ln both sides, natural logarithm both sides. Okay, so we are going to take ln both sides, natural logarithm both sides to simplify this function. Okay, so after we take, what do we get? We get like this: ln to the left equals, right, ln to the right, and our log y is the left. X raised to the x power is the right. Can you see? This is take a natural logarithm both sides. The second term, the right term, we can simplify by using the power rule, right? We can take the power x down, and let me highlight it here. We can use the power rule. Okay, we have the power rule of log to simplify the right. Okay, and after simplify, the left is lny. So the right is x times, can you see, ln at x. So now what do we get? We get the implicit equation of y. And how do you find the derivative of y to x? Of course, differentiate both sides. Now, you know, it's normal. We did it before. And we have to differentiate both sides. Okay. Of this implicit equation. Let me write the steps. Okay. We use Leibniz notation, right? So d dx of ln at y. This is the left. The right is d dx. Okay, and the x times ln at x. Now one by one. The first how to do. Let me highlight so you can see what. This is a composite function. Can you see? Is this composite? Okay, so this is a composite function to take a derivative because y is a function of x. Let me get this down a little. Because y is a function of x, therefore ln natural logarithm is only the outside function or the outer function, right? We have the inner function which is y, and therefore this is a composite function. We have to use chain rule. Let me highlight. So we have to use chain rule for this term. How about the second? So we are going to see how to get the derivative for the second. And the second is easy to see. Is x times ln x product. Therefore, we have to use product rule. That does make sense. Okay, I will going to use product to get the second. Let me see one by one. So the first chain rule. Chain rule, we have two terms, right? Is the derivative of the outer times the derivative of the inner. Okay, what is the derivative of the outer? Natural logarithm, reciprocal. Okay, E1 over u. U is y. 1 over y. This is the derivative of the out. So the derivative of the inner is easy. Just the dy dx. Okay, I think you are familiar with this, right? Chain rule. Now we're going to the right. The right is just a product. We're going to take a derivative to x is 1. So we have 1 times ln is ln did the first plus x times derivative. Let me write down. Derivative of the second term, natural logarithm, which is a reciprocal. Let me go into here is the reciprocal. Almost. And then now we have the last step. The last step is going to solve the linear equation for dy dx. You know how to solve, right? Now what do we do? Is just solve. Okay, solve the equation for dy dx. Okay, and easy to solve. Just times y both sides, right? I'm going to times y both sides. So the left dy dx derivative equals. I will use the parentheses ln x plus 1 there, and then times y. And of course, we need to back substitute because y is a function of x. The last step here, I will write is just a back substitute. Back substitute for this y. Okay, for this y. So let me go into write down. Almost it for these questions. Is dy dx equals ln x plus 1 times y. What is y? Go back to see. Y is x raised to the x power. So about here is just the x raised to the x power. Here is the first question. Okay, so let me go back, go over a little bit for the 3 steps. Okay. Can you see? The first step, take L on both sides to simplify, get an implicit equation. The second step, differentiate both sides, and then we get a linear equation. The last step is resolve. Of course, don't forget the back substitute. And this is the first. Let me go into one more question to practice the method. So look at these questions. Looks complicated. Is a product the first, and then is a composite. If someone you like, you can use a product rule first, and then use a chain rule. Excuse me. Chain rule at the second step. but you need to go through a lot of steps. Okay, and here we were going to use logarithmic differentiation. You will see it's much simple. Okay, so we're going to simplify first and then going to use the implicit differentiation. Okay. So you can see now it's the same, right? The first step, what you do, take a logarithmic the both sides. I will going to take a static natural logarithm both sides. Okay, and see what do we get. I will skip one step directly to get the answer. The left is ln. The right take ln to this complicated term. Remember, is first product the rule of log. So we get plus, and then is the power rule of log. We can take it down the power, and therefore we get a linear combination. Remember that a linear combination which is 2 times ln at x squared plus 2, right, plus 4 times ln x fourth power plus 4. Okay, and if someone you forget, you go back to look at the logarithm rule, so you'll end up with 4. Now what do we do? Okay, this is an implicit equation, right? So differentiate both sides. Let me highlight it. Now is the normal way. We just differentiate both sides. Okay, differentiate both sides. This is much normal. Okay, so I differentiate the left. Can you see? Is this and that? No, is I use Leibniz notation still. Okay, dx, and add this function natural log, but it okay, and then is a linear this linear combination. We have a linear property, right, of a differentiation. So I will get this 2 times this derivative ln x squared plus 2 and plus 4 times derivative of this term ln x fourth power plus 4. Okay, good. Now what do? We have 1, 2, 3 derivative. Can we see? How about the first? Okay, the first we did before, right? This is a chain rule. This is a composite function. We have to use a chain rule. Okay, so how about the second term? The second term is exactly the same. Okay, the second term is also composite function. Okay, can you see the second is also composite because the inner function, can you see inner function is x squared plus 2. So the outer is ln at u, right? This is also chain rule. The same for the last term is also composite function. We have to use chain rule. Therefore, all these 3 terms we have to use chain rule to get the derivative. Let me see. Okay, one by one. The first, what do we get? And the first, we will get this. Okay, we did it before, so I wrote it directly. Is the outer function, the derivative of the outer times the derivative of the inner. Okay, this is the first. And how about the second? The second is the same. I will write. What is the derivative of the outer? Reciprocal. Okay, so it's a fraction. So let me write the fraction. So it's 1 over u. What's u? U is x squared plus 2 times the derivative of the inner, which is the derivative to this polynomial. What do we get? We get 2x, right? So let me write. We get 2x. Okay, so did the first term, and then we're going to the second term. Do the same way. 4 times. What is the outer function? ln at u, which is a natural logarithm. The same, we get the reciprocal. And the reciprocal is like this. It's 1 over u. U is x fourth power plus 4, right? And then we times the derivative of the inner. The inner is this term, which is what? 4 times x third power, 4 times x third power. And this is almost right. Now what we left? We left only to solve the linear equation for dy dx. What we need to do now is just solve for dy dx. Okay, so easy to solve. We need to simplify. Okay, so let me do one more step. I times 2 and 2x together to get a simplified fraction. So you will see it much better. Can you see? So the first left us the copy 1 over y times dy dx is a fraction. Okay, let me get this fraction. Is how many? Is 4x this time. The bottom x squared plus 2, right? And then plus another fraction. Yes, there. The top this time is 16 x the third power, right? The bottom is x fourth power plus 4. Okay, so now how to solve? And the y is there. We times the y both sides. Can you see? Times the y both sides, we get the solution. We're going to copy all these terms. Okay, so we're going to copy this. See, I will put it here. Okay, and then we have to do the times y, right? So times y, I will put a big parenthesis here. Big parenthesis times y. Okay, so almost right. Let me copy all this again. Let me see. The last, of course, you know, we don't leave y here. We need to back substitute. So you know, the last is just the back substitute. Okay, because we know y is a function of x, we need to back to y. So can you see this? The back to y. Okay. How to back? Let me copy all this again. Okay, so the last so we need to do is just plot y, right? So plot y, we don't need the. Let me get this. Okay, good. So I will erase this, and then to plot back to y. You know, y is a very complicated function. Can we see what is y? Y is all this I have to type. We're going to write all this y to here. Let me use this color. So you see back substitute was y. Y is use this color. So y we just see. Okay, it's a big term. Let me write this big term, which is x squared plus. So we're going to see the plus this. Okay, so plus what? Plus 2 and the second power, and then x4 plus 4 raised to the fourth power. So this is the last. It's very long. However, the steps is easy. Okay, it's implicit logarithmic differentiation. Whatever the first is simplify, and then the second take a derivative to both sides. The last step is solve, and also don't forget back substitute. And this is the two questions. Now I will going to use the logarithmic differentiation to give a proof for the general power rule we learned before. Can you see here? And if someone forget, you can review refer to the videos before. Okay, so here when we learn the power rule at the very beginning of this chapter, okay, but we did not prove the general power n, right? What we proved? We proved for the positive integer n only, okay, at that video. So now we can prove definitely use what we learned just. First we have a function. So if we have this power functions, how to do. And this is not difficult. If you practice the last two questions, now how do you find the derivative? No matter n is any number, any real number, okay, what do we do? Take a logarithm both sides, right? Okay, so I will going to do this question. Now is just a take. Okay, so I will going to take a natural logarithm both sides again. And then see what do we get. So I will use this. I will get the left is ln at y. The right, and this power rule of logarithm, I can take it down the power. Okay, so this time is ln at x. Okay, now is the implicit equation. And then what do we need to do? And take a derivative to both right sides, or differentiate both sides. We can differentiate both sides. And then what do we get? You can see our rod complete. So d dx at ln of y equals the right take a derivative. Of course, n does not matter. So we need to do this. And ln x take a derivative. Of course, now what do we do? And the first is chain rule. Can you see here? And we did a lot of times. This is a chain rule. We have to use a chain rule for that term. Okay. I will write down what is the answer. The outer is a natural logarithm. Take a derivative is a reciprocal function. The inner, of course, is dy dx. Can you see? And then the right is n times. The derivative is reciprocal of itself. Can you see? Now is what? Is a linear equation. We just solve the linear equation. Okay. We just solve for dy dx. This is the last step, right? Okay, so we're going to solve for dy dx. Just times y both sides, right? So I get dy dx, which is the derivative of this power, okay, function equals what? The fraction n over x times y. Times y both sides. And then I plug y back, okay, what is y? Y is x raised to the nth power. So now you know we can cancel. We can simplify, get what? N times x raised to the m minus 1's power. And can you see? This is the final. Is this the formula we learned before? About the power rule. Definitely. Can you see? And the power function, take a derivative, goes to what? Take down the power. And then the new power is the old minus 1. Okay, so this is the proof. The super easy, right? If we have this method. So this logarithmic differentiation is powerful. And I will show you one more. Here. The last. And this, do you remember we defined the Euler number or natural number before, but we do not have this limit formula. All right, you can see this limit is very strange. Okay, and 1 plus x is very small, so this is just 1, and the power 1 over x is infinity. Or you can say is like a 0 or 1 raised to the infinity. This is very, very strange limit. However, this limit exactly gives us e. Okay, and now we were going to prove the first. Okay, and we will not use we will not use the logarithmic differentiation because we do not need to find the derivative, but we do use the logarithm, the first step idea. Okay, we use the logarithm to simplify this limit and then to find the derivative or to find the limit. And why we have the second? Okay, the second is just a special case of the first. Okay, why? Can you see? The second is no longer x, right? Here is x, but here is 1 over n. Okay, 1 over n is just a special case, so you can do what? If we simply do this substitution. Okay, so let me put if I use x equals 1 over n, can you see we put log? If we put log x is 1 out of n into the first formula, definitely we will get the second. So here is 1 over n, so the reciprocal is n, and then when x goes to 0, n of course goes to infinity. Can you see? Okay, so the second is just a special case. All we need to do is prove the first. That does make sense? Okay, so the first I said we will use log to simplify. That's all the idea we need. And so let me set up. Okay, so now we're going to set up something. So let me set up f(x) is the function for that big term, which is 1 plus x raised to the 1 over x power. Okay, if I set up this, and then we take a log both sides. Okay, so we can do this. We can take still ln both sides. Do you remember this big idea? Because logarithm can help us to simplify this power. Okay, our purpose is to find the limit of this function as x approaches 0. Okay, but we can do this. We can take ln first. After I take ln is this ln at fx equals what? The power can take it down, right? That's a power rule, and then we will get a fraction to the right. That fraction is much simple. Okay, and the top is ln at 1 plus x. The bottom is x. That does make sense because 1 over x times ln this is just a fraction. Okay, so now it's much easier. We need to find the limit of f. We're going to find the limit of ln at f, which is just a fraction. Okay, so all we need to do this. Now we're going to find the limit. Find the limit of this first. ln at fx. Okay, after I get the limit of this, I will go back. I will show you how to link it to the limit of f. And this should be equals, this time is the limit x approaches 0 as x approaches 0 is this, right? I will going to get this fraction. Is x on the bottom, and the top is this 1 plus x. Okay, so not much. It's a little bit hard to find this limit. Okay, so how to find that limit? A little bit of trick. So we have to link this limit to the derivative of a natural logarithmic function. Someone say, why is linked to the derivative? And the top is delta y. Okay, so it's only one function, and but I can put one term. So can you see? I put this term. This is a little bit of trick. I put this term here because L1 is how many? Is 0. I will put the 0 to the top. So we have two terms. Can you see? I put it like here. So what do we have? We have the limit x approaches 0. Now I will get a little bit longer of the fraction. Okay, the bottom is dx, but at the top we can put something there. I can minus. Can you see? I minus ln at 1. Did we change anything? Because this is 0, so we did not change anything. But this time, can you see, is this the derivative of the natural logarithm? Yes, this is the top is delta y, and the bottom is delta x. Okay, someone will say it's not h. No problem, so we were going to change to the definition. Definitely. Let me just do this. Okay, so let me copy. So we have the limit. Can you see? X approaches 0. I will don't put the x. Okay, so I will put another. H approaches 0. Okay, I change x to h. All you say is substitute. Okay, now it's still the same. What do we have? We have this fraction. Okay, the bottom this time is equal to what? And we say, no, sorry, the bottom we need to go to h, right? Okay, and then what is the top? The top is ln at 1 plus this time is h. Okay, and then it's minus ln at 1. Now what do we do? It's exactly the definition. Can you see here? This is exactly the definition of the derivative of natural logarithm at what? At the point 1. That this makes sense? Delta y over delta x. Delta x is h approaches 0. The derivative definition. Okay, so now let me write it down here. And this is the derivative. The derivative of what? Natural logarithm. Okay, at 1. At x equals 1. Okay, so let me put this bar. At x equals 1. That this makes sense. This is one of the notation, right? Okay, so what is derivative? Because we know, I just plug the derivative. The derivative is reciprocal, right? And then we put back x at 1. Okay, so x at 1. Plug back 1. 1 over 1 is what? Is 1. Good. So let me go back a little. Can you see we get the limit of ln at f? Now we go back to the limit at f. The limit at f. Okay, so a little trick. Can you see here? The last step we can do this. Okay, so our purpose is going to find the limit of f, but we do have the limit of ln at f. All we need to do is use this inverse rule, and you learned this from trigonometry before. Is put the base e, and then the power is ln at fx. Do you remember this? What the name? Okay, e the same base, so we cancel everything. We call the inverse rule, right? This is the inverse rule of logarithm. We learned that before. Okay, so now I can do what? I can plug the limit to the exponent. Okay, can you see? So here is ln at fx. Why the limit can go to the exponent? Because the exponential function is continuous. Always say the continuity of exponential function. Okay, now the last you know, because we find, okay, what is that limit? So is 1. So we plug 1 back here. So 1's power. Okay, this is 1th power. Therefore, the final answer is E. Can you see? This is the proof for that famous formula. I'll go back a little. We finally find the limit of f is E, natural number E or Euler number E. Okay, so this is a very famous limit. So you can go on to verify this by evaluate x. Take a lot of x approach 0. And build a table. You can see exactly approach to 2.712 like that. Okay, which is the natural number E. And that's all. That's all for this topic. Okay, thank you. If you have any question about this topic, please leave your comment. If you like this video, please give me a thumbs up. And you are very welcome to subscribe to my channel for more videos. Thank you for your support. And the next video, let's see. Okay, here. And we are going to deal with the related raised problem. Okay, so I hope to see you there. Thank you. Have a nice day. Bye.